this lesson or miss this lesson, I'm going to talk you through the notes here for the integral as an antiderivative. So we did a couple of warm-up exercises where we differentiated and two where we antidifferentiated or found the antiderivative. In both cases, we had to use the condition that this point has to be satisfied by the antiderivative, and this point has to be satisfied by the antiderivative. Thus, we solve for our constant of antidifferentiation. And what we want to talk about today, big idea, is that integral and derivative / integration and differentiation are inverse operations. So what we see here is if we take the derivative of a definite integral, we end up with the integrand. And if we think about inverses that we've dealt with before, we would do this composition of functions to end up in our argument. It makes sense that we end up at our integrand here. Like we discussed previously, we need to have these variables of integration match, but in this case, the limit has to be a different variable than that variable of integration. I kind of wanted to see how we could look at our definite integral in a different way. So we're going to let f of x be an antiderivative. And it's typical to use an uppercase letter to denote an antiderivative. And I'm going to make the argument that this definite integral is also an antiderivative. And that makes sense because if we differentiate an antiderivative, we should be back at our integrand. So I'm going to add that constant of antidifferentiation, and I'm going to solve this equation for C. I get that C is this definite integral, subtract the antiderivative, and then I'm going to let A equal x, because I know one of my integration rules is if I have a definite integral that starts and stops at the same spot, then its value is 0. So then this tells me my constant of antidifferentiation is really this minus f of a. So I'm going to substitute that in from the very beginning, and I have what our definite integral is defined to be, and that is any definite integral is the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And we're going to do a couple of examples. So how I would start this problem, and what I asked you to do the other day was to sketch it, to define the area by shading and then use some geometric formula. Well, there is no geometric formula for this area, so now I have to evaluate it using this new information. So I need to find the antiderivative of my integrand, and I'm going to reverse the power rule to do that, and then I'm going to check by ddxing this. For taking the derivative of what I believe to be my antiderivative just to check that I get back to my integrand, and I am correct. Now the notation that I must use is I take the antiderivative and the elongated s disappears, just like when you extract a square root. That square root symbol disappears, but now we replace it with this bracket, and we put our lower limit, upper limit, and then we substitute and evaluate. So I'd have 3 to the 4th over 4 minus 1 to the 4th over 4, which gives me 84ths or 20. So the value of this definite integral is 20. All right, our second example here, again, I'm going to start it the way I was doing the problems the other day, sketching out my parabola, highlighting that area from 0 to 1. I notice it's underneath the x-axis. I'd be tempted to use the semicircle, but I know I can't because this isn't a semicircle. This curve is not generated by the equation of a circle. It's generated by a quadratic. So I'm going to find the antiderivative. I'm going to check by taking the derivative of my antiderivative, and it is correct. So now I'm going to get rid of the integral symbol and write my antiderivative, and I'm going to evaluate it at the lower and the upper limit. I am going to ask you to do the substitution here for the lower limit, and also to use parentheses when subtracting so that you subtract every term of your antiderivative when there's more than one term. I'm asking you to substitute the 0 because there are cases where a function evaluated at 0 does not equal 0. For example, cosine of 0 equals 1. E to the 0 equals 1. So you want to make sure that you don't make a mistake and leave something out that you should be accounting for. And this antiderivative evaluated at the upper and lower limit is a negative 2/3, which makes sense because I see that that area is below the curve. Our next one here, we want to think to ourselves, what would we differentiate to get secant x tangent x? And it is the secant of x. And now we're going to evaluate it at the upper limit and lower limit. I like to think of secant in terms of 1 over cosine. So the secant of pi would be 1 over the cosine of pi, which will be -1. The secant of 2/3 pi, 1 over the cosine of 2/3 pi. Now, 2/3 is in the second quadrant, so I know the cosine is negative there. My reference angle is pi over 3. I know the cosine of pi over 3 is 1/2. Then I have to take the reciprocal. That's how I get this -2. And then I have -1 minus a -2 to get +1. Our last example here. I have the sine of t. Originally, I thought, oh, the antiderivative is cosine. But I see when I differentiated that, it is not correct. So I have to update my thinking process. And I give the cosine function a negative. Then I differentiate. I get the opposite of the opposite, which is a positive sine t. So now I have the correct antiderivative. I'm going to evaluate it at the upper limit minus the lower limit, and our answer could look like any one of these 3 possibilities here.